nuestra charla del día de hoy. Para eso, pues agradecemos a todas las universidades participantes, como es la Universidad Nacional Mayor de San Marcos, la Universidad Federal de Río de Janeiro, la Universidad Federal de Pernambuco, la Universidad Nacional de Colombia, la Universidad de Barranca, el CIMBESTAF, la Universidad de Pelotas, entre otras universidades que tenemos el día de hoy. Agradecemos por favor a la gente en el público ir dejando sus preguntas para que al final de la charla pues podamos contestarlas con nuestro palestrante del día de hoy. El día de hoy tenemos a el profesor Stuart Holmes, que él, bueno, lo voy a decir también en inglés. Today we have a Professor Stuart Holmes. Stuart Holmes got his PhD in 1988 from Imperial College. He then moved to New York, USA, with a NATO Science fellowships for 2 years. After that finished, he moved to Cambridge, and actually he worked there for many years in collaboration with Professor Crispin Barnes and Professor Michael Pepper. And actually he now works as a lecturer in electrical engineer at University College of London. It's a pleasure for us have here Professor Stuart Holmes in this talk. Professor Stuart, now is your moment. You could start your talk.
Thank you, Ximena. Good morning, everybody. Let me share my screen with my talk. Sorry, let me just try again. Is that visible?
Yes.
Can you see that? Okay. I will start. Sorry. I've got such a small screen here. I'm just having difficulty. Let me just try again. Ah, that's better. Thank you again for inviting me to give this talk. And I want to tell you about what I've been doing recently. I've actually just been at the University of California for 2 weeks, and this has been funded. And I want to tell you what we were doing there, and also what else has been going on in the lab in the last few months. We did have a visit last year from Ximena, and we started some of the work I'll talk about was started when she was with us in Cambridge. Okay. So, as I said, I spent 2 weeks at the University of California and working in Santa Barbara, where there is a quantum foundry, and we were funded by the UK government to have this short-term collaboration, and the goal there was to develop quantum technologies for fundamental physics discoveries, and then apply those quantum technologies for fundamental physics into a range of sectors where appropriate. So this is kind of the language that was used to describe the formal research program with them. What I want to tell you today is how we make suspended semiconductor structures, how we make disordered structures by focused ion beam damage, how we can make multi-connected structures. We did actually hear some of that work last week in the talk last week. There was a talk on multi-connected superconductors that can go insulating. So there's a kind of a link up with that work, although from this point of view, we're coming from the semiconductor side. If I've got time, I'll also tell you about tin and bismuth materials. And these are they're fairly new materials. In thin film form, they form topological insulators. So tin we think of as a metal, but in thin film form, when it's grown at low temperatures, it behaves like a semiconductor, zero band gap semiconductor. So the overall aims of these projects are controlling the electron spin through spin-orbit coupling, and applying electric fields to move the wave function in the crystal, so-called gating. Also increasing spin-orbit coupling effect called the Rashbar effect. So the Rashbar effect is a spin-orbit coupling effect that can happen when you have interfaces and asymmetric potentials caused by doping or heterostructures, particularly in high mobility systems. A lot of these material systems are quite low mobility. We're hoping to push the mobilities up into cleaner systems, but still be able to control the spin-orbit coupling effect. We also want to try and make thermally isolated devices. So in a thermally isolated device, you have to pattern the device and then remove the substrate. So it's kind of freestanding, and the freestanding thickness might be 100 nanometers. So they're very fragile devices to work with, but we've developed the technology for that. There we go. So this is the device that we were hoping to make whilst we're at the University of California. It's actually published. Some of the work is already published. It's called a spin FET device, spin field effect transistor device. And the image on the left here shows an SEM image looking down on the device, looking down on the device. And it shows a series of metal gates. We have the gates on the left-hand side of the device, the gates on the right-hand side of the device, and then a central gate region called a mid gate. And the idea with this device is that we can tune the current. There's a kind of a voltage, you can kind of see the external circuit there. There's a voltage source. We measure a current, we apply a voltage, we measure a current. We can also apply DC voltages to the circuit. So what happens on the left-hand side of the circuit is we apply a negative voltage to the gates. This forms a 1D channel, one-dimensional channel, and we can control the spins in that channel. The electron spins then travel through the device. There's an electric field. They travel through the device, and they enter the right-hand side of the device. The right-hand side of the device is so-called spin selective. And so the right-hand side of the device can sense which electron spin is coming through. Is it a spin up or is it a spin down? And the device itself is controlled by applying a voltage to the midline gate here. So when there's a voltage on the midline gate here, we can rotate the spin around. So if the spin is traveling through the system, we can rotate the electron spin around. And that's shown in this data here. So the data on the right-hand side is this detector voltage. So that's the voltage that appears on the right-hand side of the device as a function of midline gate voltage. And as we apply the midline gate voltage, we rotate the electron spin. However, when we've got the red curve here, that's set up so there's no spin. There's no spin. We haven't removed the degeneracy between the spins. So we have both spins that rotate round. So there's no spin selectivity. However, when we apply an asymmetric gate bias to the left-hand side, that's in the lower diagram, then we see this, we can just pick out one spin and rotate the one spin around. So for example, if one spin comes through the system and the system is set up to measure the opposite spin, that spin is just reflected to ground. and collected as a current to ground. So we've got a very, very powerful way of making a field effect transistor. So this device, it relies on ballistic transport, so we have to have low disorder, high mobilities. We also have to be able to understand how the gates operate in these systems, how we can control the wave function with an applied gate voltage. We also have to understand how this spin-orbit coupling effect occurs, how this Rashbar effect occurs, how the confining potential asymmetry, how does that relate to the spin-orbit coupling? So that's the basic device that we're trying to measure. Oh, I'm sorry, I skipped a page there. So these are the wafers. This is a diagram. This is one of the wafers that was grown in Cambridge University by Chong Chen and Ian Farrer. This is a kind of a sandwich structure, and this is how the structure is put together. We have this is the surface on the left-hand side. This is the surface. We put down an insulating layer on the surface. We then have a quantum well, so-called quantum well, where the red line is there, that's the wave function. So the charge is just confined to a very, very thin two-dimensional sheet. Then we have the buffer layers, and we have this strongly graded layer. The inset here is a blow-up of this device. So this is the confining potential now. This is energy on the y-axis as a function of distance from the surface. And the charge itself is just confined to the two-dimensional region here. What we found in this work is that these are very, very complicated structures. They're difficult to grow. We've got the compositional grading in the structure. However, what we've done recently is to completely etch away the substrate. So we completely etch away this material at the back. So we make a device and we etch away all the material at the back. And we found that we don't degrade the mobility after removing this buffer layer. So the buffer layer was originally put in to minimize defects, create a nice clean system, but we found we can take most of that away and do not degrade the electrical properties of the wafer. So we can then look at this spin-orbit coupling effect electrically in these suspended layers. We're also measuring the Hall effect, how there is actually a lot of structure in the Hall effect. We can also try and improve the mobilities in this system. We can insert very, very thin quantum wells that have different spin G factors, different spin properties. Okay. So some of this work we published. Chong Chen and I did this work in 2020. So just before COVID came, we got this work. And what we published in this work was, in fact, you can see an SEM image here. So this is an image of the device. This is the channel. This is the conducting channel. These are arms, potential arms for measuring voltages. And it's come up above the substrate. We've etched away underneath the substrate. And what we did in this work was to demonstrate a thermal isolation. And what happens is when you apply a current to these suspended layers, because there's nowhere for the heat to dissipate, the electron temperature rises very rapidly, and we can measure that. We can measure that electrically. So this paper that was published in Applied Physics Letters, we demonstrated very clearly that these suspended layers were thermally isolated. Okay. We've also, more recently, we've done measurements. These were taken, I think, last year, I think. These are SEM images of some devices. It's quite nice. You can make these structures, and they're very, very close to just failing. So you're etching them away, and they're suspended. Sometimes they just collapse down. Sometimes they break. And these are just a kind of some of the images here. You can see in the image here, it's a freestanding channel, but the channel is just cracked. Also, likewise, we can see here. This is the a cross section through the channel where we've cleaved, and you can see how the etch can kind of etch away underneath to make the free suspended layer. The image on the top left here was a device that had failed, and you can see where the device had lifted off from the substrate, but had then kind of sheared away and cracked. So it was a very useful study to do, to find out how thin we could make these layers. In fact, turns out these layers are kind of strained, so there's an inbuilt strain into the layers, and the strain stops them collapsing. So what we did to advance this project is, instead of having these graded layers at between the substrate and the two-dimensional quantum well, we put in a sacrificial layer, purposely put in a sacrificial layer. So this diagram here shows the confinement potential as a function of thickness. This is the surface. We've then got the quantum well made of gallium arsenide. We've then got other structures here. We've got buffer layers, we've got doping. We've then got this thick sacrificial layer made of aluminium gallium arsenide, and it's 66% aluminium gallium arsenide, and that's very, very reactive. When we put this structure into HF acid, the HF acid attacks preferentially this sacrificial layer. And if you put this structure in an SEM, so the image on the right here is an SEM image, you can see where the etch has completely undermined this sacrificial layer, and we're just left with this freestanding structure, which is 120 nanometers. So we can make these things 120 nanometers. Okay. Oh, I'm sorry. My computer's running a bit slow today. Apologies. It's not very reactive. We can also we also discovered how large a structure that we can make and keep it suspended. When you've got a 1 micron thick active layer, they're easy to suspend. You can suspend them over tens of microns. When we've got a structure that's 120 nanometers thick, we can suspend it over about 8 microns laterally. So these are some SEM images. They're obviously devices that have failed in some way. So this device here, you can see we've etched away underneath, but it's collapsed down. The active region where the two-dimensional electron gas is has kind of collapsed down. Also, there are other structures here. As I say, we've kind of worked out how large we can make these structures, and so they don't collapse down. So, excuse me. Why do we want to do this? It seems counterintuitive that we can make this nice high mobility two-dimensional electron gas system, and then we etch away all the material in a sense that's made it a two-dimensional system in the first place. So what we were trying to do with this material is to introduce a control disorder, and hopefully the system would break up into a so-called non-ergodic system. So we would lose if we had thermal isolation, we'd lose contact with the outside contacts. And if it was disordered, it would go from a diffusive conductivity region. So this, when the transport is not disordered, it's so-called diffusive, and charge diffuses through the system. We describe that as we describe the conductivity as n e squared tau over m star, where n is the carrier density, tau is the elastic time constant or scattering time, effective scattering time, and m is the effective mass. When we introduce a disorder into the system, so we can introduce disorder in many ways. We can ion beam damage them. We can put doping in there. That creates this disorder. We get something called a mobility edge. When we have a mobility edge, this diagram in the middle here shows the density of states in the conduction band as a function of energy. And when we're in the middle of the band, we have conducting states, we have a mobility edge. When the chemical potential or the Fermi energy is below the mobility edge, we have to thermally excite carriers up to the mobility edge to measure the conductivity. So we have a kind of an exponential dependence on conductivity. This was covered last week in the talk by Professor Granato last week. This aspect was covered. What we see in these systems, or what we should see in these systems, is that the system goes over to hopping. So we have a temperature-dependent conductivity with a characteristic energy to the mobility gap of T0 as a temperature. And there's some power here. There's some power that comes, a power law that comes in. So when we have this hopping, we have this slightly different temperature dependence. If P is a half, it's variable range hopping. We can also get 1/3 in, we can also get a power law of 1/3 for different types of hopping. What's also interesting in this system is that the prefactor sigma naught is quantized. It's quantized to the quantum of conductance. It's E²/h. When we have Mott variable range hopping, so P equals 1/3 for Mott variable range hopping, it's about 2E²/h. So even for different hopping mechanisms, we still have this quantized conductance. So once we go over to this thermal isolation system and we take away the phonons, the lattice can no longer vibrate. The question is, do we still have a hopping effect? Does the hopping disappear as well? Do we go to zero conductance when we have thermal isolation? So that was the main reason for removing the substrates, putting in disorder. Do we have a new state of matter where the conductance is zero and also the thermal conductance is zero? So the system is totally isolated. It can't communicate with the outside world and goes over to being a kind of a non-ergodic system. Sorry. I'm sorry, my computer's behaving very, very poorly today. So this is a typical structure. It's freestanding. It's an SEM image. The scale bar there is 10 microns. So it's not the smallest structure. It's a few microns across. You can see we've etched away underneath. Some of the etch has come through and destroyed the device. And we just get these little pillars here that hold up. There's a kind of where it's etched through, we just get a small pillar underneath that holds up the system. We can apply voltages. We can apply AC voltages, DC voltages. We can measure currents. We can also, we've got a top gate on here. So we're actually, the SEM image here is looking through a top gate. So we can apply gate voltages and change the carrier densities in the system. Also move the chemical potential around in the density of states. So we have disorder, we have thermal isolation, we have low electron temperatures. When we measure the conductance data is here. This is now the device conductance as a function of top gate voltage. And what happens is the device is totally depleted of charge, and we need a positive gate voltage. We apply a positive gate voltage to the top. This switches the device on, and we can measure a current. We can measure a conductance in the device. So when the device is conducting, we've got conductances greater than E²/h. When we reduce the carrier density with the gate, what happens is the system breaks up into a series of islands. So it becomes non-ergodic, but it's breaking up into a system of little electron puddles. So what happens is the current or the conductance or the current through the system is just a transport between these islands of charge, which is a so-called Coulomb blockade. So it goes over to being a Coulomb blockade system, and we see this kind of inhomogeneous behavior. We don't see this variable range hopping transport, even though we've set the system up, we've put disorder in, we've set the system up. So we should go over to, we're at low temperatures, we're at low electron temperatures, but the system goes over to an inhomogeneous system. What we also see is when we're at high conductance, so that's when we've got lots of carriers in, we tend to get conductance fluctuations. So the system is behaving in a very, very different way to what we were expecting. It goes over to conductance fluctuations. Okay. This is a summary of a real device here. This device here, it's 120 nanometers thick. It's freestanding. We've measured its resistance or conductance. And what I wanted to introduce into this system was the effect of electron spin. So we have this disordered system. If we have a disordered system, we have the spin properties are determined by the Dyakonov-Perel spin scattering mechanism. So if we have this mechanism operating, if we have a disordered system, the spin scattering rate is very low. So the spin scattering rate, tau here, 1 over tau, is determined by the Rashba spin orbit coupling effect, and Tm. So Tm is the elastic mean free scattering time, which can be very low in these disordered systems. This time is very low, which means we get a very, very low spin scattering rate. So electron spin in these systems must be much more visible because it's got a strong spin lifetime. So that was the idea with this system. As I say, what happened in this particular device is if we apply a DC voltage now, so this data on the false color image I'm showing you here, the y-axis is DC voltage, so that's DC voltage applied across the ends of the wire. The x-axis here is the top gate voltage. As we put charge into the system, it starts to conduct, but we only get this Coulomb blockade. So what I'm showing you here is the color here is the current flowing through the system. So we can only get a current flowing through the system when we have the condition for a Coulomb blockade. So that's determined by this gate voltage. And we have something called a charging diagram. So what happens is when we apply a DC voltage in millivolts, is we change the chemical potential in the source and the drain contacts at each end of the suspended wire. Okay, so we get this so-called these kind of Coulomb diamonds. So it's a kind of a demonstration that this system is behaving as a series of anisotropic quantum dots. Now, it might be that spin is important in this system, but what's more important is we just limit the conductance is just limited by this Coulomb blockade effect. So just to summarize this part of my talk, I introduced the spin FET device. I introduced the suspended indium gallium arsenide structures. I talked about this thermal isolation test where we can really demonstrate we've got suspended layers. Enhanced spin orbit coupling in these materials, although it's more of a kind of a wish. We were hoping to see enhanced spin orbit coupling in these materials. In the suspended layers themselves, we have the universal conductance fluctuations at high conductance and at low conductance, where the chemical potential has really dropped into the tail of the density of states. We see a Coulomb blockade effect coming in, and the system behaves as if it's stochastic. So we know we're going to get this behavior. We just can't predict when or how. So the system goes over to being stochastic. It's also non-ergodic, but it's not non-ergodic because of this zero conductance, zero thermal conductance behavior. Okay, so I'll just move on to the second part of my talk, and that's developing the theme of disorder. And we've moved over to a different material now. We've moved over to indium antimonide, and this is a kind of a cross-section of the device. We published this work in I think last year we published this work, or 2022 we published this work. And this is a kind of a cross-section of the device. We were hoping to get some suspended layers in this material, but we haven't developed the processing of this material system yet. And the indium antimonide is a narrow bandgap semiconductor. We put some manganese doping in there to make it p-type. Manganese is a p-type dopant, indium antimonide. And then we put down a layer of insulator and then a top gate. So with a gate voltage, we can induce charge at the surface or perhaps deplete the layer. And the original idea was to apply magnetic fields. Now, the electronic G factor in this material is very large. Applying magnetic fields makes a very large difference to the conductivity. The conductivity can go over to hopping in a magnetic field. So that gives us a kind of a tunability of this hopping effect. However, reality was slightly different. What we found was, this is a kind of a plot now of device conductance. So the red color is device conductance. On the y-axis, we have magnetic field. So this is 0 to 8 Tesla. On the x-axis, we now have gate voltage. And what happens with a positive gate voltage is we induce a charge at the surface. So we just have a surface conducting layer. The rest of the device is kind of disordered. It's got the manganese doping in there. And if we look at a simple, this is fixed gate voltage 25 volts. If we measure the device resistance as a function of magnetic field, we see this kind of increase in the magnetic resistance and then this oscillation. And this oscillation is the Shubnikov-de Haas effect. So what we see in this material is we have a very, very highly conducting surface region and then a disordered bulk region. So we started to use these devices to look at disorder, but we knew that we would have this highly conducting surface region depending on the gate voltage. What we then did with this material was to disorder it, to introduce disorder deliberately. Initially, we didn't want disorder in there. We just wanted some manganese doping to make it slightly p-type. Manganese is a p-type dopant. What we found was with ion beam damage, then we could create disorder using damage. So this diagram here on the left shows device conductance. It's plotted on a log scale because we have a very, very strong change in device conductance. The x-axis is gate voltage. So at positive gate voltage and no damage, that's the black line here. We go from a 2D region, we're dominated by the 2D region at the surface, back down to a 3D region. So as we change the gate voltage, we have charge at the surface, and then we just have this 3D region in the bulk, in the disordered bulk. Then as we introduce ion beam damage, so this is gallium ion damage, as we put more damage in, the conductance drops down, and eventually we just lose this surface. We lose this surface, this high mobility on the surface. And the diagram on the right here shows the device conductance as a function of ion beam damage. As we put more damage in, the conductance drops down. So the purple color is when we've got the surface region, the 2D surface, and then the black is just how the bulk changes. We've got no 2D region, it's just the bulk. Okay. So a little bit more information on these devices. They were 100 nanometers thick, so they started at 100 nanometers thick. They're grown on gallium arsenide. They kind of have a quasi 2D, a quasi 2D behavior. And we use gallium ion beam patterning at 30 kilovolts. What we find is, if we measure the conductance in the disordered region, it goes over to this MOT variable range hopping. So with introducing this disorder, we can go over to this situation where we have this hopping behavior, and the device conductance follows this exponential behavior now with a kind of a mobility gap, but with a quarter power there. Okay, if we look at the actual experimental data, on the left here we have device conductance. Again, it's on a log scale because we've got changes over orders of magnitude of conductance as a function of 1 over t to the quarter. So I plotted it as 1 over t to the quarter. Obviously, 1 on this scale here is 1 Kelvin. Okay, and as we put more without disorder, we just get the curve here. There's no temperature dependence. It's just an extrinsic semiconductor, slightly disordered. As we put disorder in, we find that the device conductance comes down to the quantum of conductance. It comes down to E squared over H. And then, as we put more disorder in, we start to get this exponential behavior. So the device goes over to variable range hopping. Now, if we plot that out again as a function of T0 over T, so T0 is a characteristic energy associated with this hopping process, it goes over to a kind of a universal behavior for this effect. So although we've started with a very, very high carrier density, we've been able to introduce this variable range hopping effect. And this diagram here just shows a little bit more detail about what's going on in these wafers. We have ion beam dose here on the x-axis. And so for low dose, what happens is in the device, we have a kind of a Nyquist noise going on in the system. So that's kind of an inbuilt electronic noise. And that's the kind of scenario we wanted to be able to study this variable range hopping effect without phonons. So if we take away the phonons from our suspended layers, can this Nyquist noise, this kind of fundamental electronic noise, create a hopping effect? So that's what we were hoping to see. What we also find is at very, very high doses, these are very high doses now, 10 to the 16, 10 to the 17, we tend to introduce so-called RTS noise, which is random telegraph signal noise. So we see this kind of this two-level switching behavior coming in, which masks any form of electronic noise. It's very dominant. So again, sorry, I'll just take a small drink. So we've got this system now, this indium antimonide. It's not suspended. We've still got an anchor to the substrate, but we can introduce damage in a very, very controllable way. So again, this is kind of the same data. This is dose level here. This is ions per square centimeter. So it's a dose of gallium ions. It's done in an SEM system. It's a nice system for creating disorder. And I'm just going to show you a set of devices where we've put disorder in the kind of this kind of red rectangle here. So we're in this variable range hopping. As I say, if the disorder's too high, we can pattern the material. We're actually patterning the material. We're actually removing material. And you can get things like nanopillars. You can get quantum dots on nanopillars. Okay. And as we developed this work, we started to ask the question, could we measure a wave function? Could we look at interference between wave functions in this system? If we're in the hopping regime, could we perhaps see some kind of phase coherent interaction between the wave function, in the way that was reported in the LAFMAT talk last week? And so I'll just I've just picked out a paper from the literature. It's called, it's actually work done by Professor Shavin's group in Russia in the 1980s. And what his group did was they evaporated lead telluride onto a grid system. And so it opened up kind of holes in the system. It was multi-connected. And what happened was he was able to measure phase coherent oscillation. So as charge in this system went around the grid, it would interfere, and the interference would be driven by the magnetic flux in the grid. So he demonstrated very nicely that his devices went over to hopping. This is his experimental data here on the top left. This is logarithm of device, logarithm of resistance as a function of temperature. It follows this MOT, so-called MOT variable range hopping for 3D. When he applied a magnetic field, he could see this phase coherent oscillation in the system. So although the charge was hopping, it wasn't a ballistic effect, it was a hopping effect. He could still see this phase coherent behavior. And as he changed the phase in the system, so phi here is a magnetic phase in comparison to the fundamental of flux. As sorry, let me rephrase that. What he saw was this cosine dependence of his of the interference. Phi there is the magnetic flux in comparison to the fundamental flux H over 2E. So I discussed this work with several people who were involved in the early stages of this work. Professor Boris Altshuler, who's at Columbia University in New York, and Professor Igor Lerner, who's in Birmingham University. We had some discussions on this, and this is my attempt at kind of getting to where the Russian work had finished. So this is my device here now. It's an indium antimonide focused ion beam damaged system, 1.8 times 10 to the 14 ions per square centimeter. So I know it's right in that region between Nyquist noise and random telegraph signal noise, and we're right in the region where we see the variable range hopping. Here is an SEM image. You can see the hole bar. You can also see where we've etched the holes in here, and the holes are about 0.5 micron in diameter. And this is the experimental data here. So this is device conductance now as a function of magnetic field. It's all happening at very, very low magnetic fields. This is device conductance as we sweep the field. This is an upsweep, the red curve, and the green is a downsweep. What I've actually done here is I've swept the field many, many times in each direction and just added the signal together to reduce the random noise level. Because what happens here is, as we sweep the magnetic field, the temperature changes. And if the temperature changes, you've got an exponential dependence of your conductance on temperature. So experimentally, this is a very, very difficult measurement to do. Anyway, after some persistence, we're able to see this phase coherence interaction here. So as I say, the phase comes from the magnetic field and the area. If we calculate the area, the area here is something like 0.5 micron. This is the actual area. It's about 0.5 micron square. So each bit is 0.5 micron across. And if we calculate from the period of the oscillation here is something like 10 millitesla. If we work out what area that gives us, it gives us about 0.45 microns. So it fits very, very well with the lithographic area of the device. So we were quite pleased with that, and we're hoping still to develop this technique. So just to summarize this part of the talk, I mentioned that we can enhance the surface conductivity in indium antimonide. It's very, very difficult to deplete it because the background carrier density is so high in this material. What we also haven't done is we haven't got the thermal isolation yet. We want to develop the thermal isolation in this material system. we can introduce this, we can induce this hopping conductivity effect, which is essential for looking at localization effects. We've got these multi-connected devices now, these kind of anti-dot systems, and we've started to see these phase coherent oscillations in this disordered regime. So the electron hops around the structure, but it still retains the phase. We can still pick out the phase, even though it's in the hopping regime. That's this so-called Altshuler-Aronoff-Spivak oscillations. I won't mention the last point there. I was going to mention the last point, but my colleagues in London are studying electron heating effects in these systems. So they do the same measurements, but they apply a higher current. Apply a higher current, you heat up the electrons inside the system. So they're looking at that. The system becomes bistable. The system eventually becomes bistable. So I'll just move on to the last part of my talk. I'm just moving my things on my screen around. So as I mentioned in the introduction, I wanted to tell you a little bit about tin and bismuth. These materials are grown in the University of California in Santa Barbara. When we started this work, Ximena was in the Cavendish lab for some time. We started working on this together. We've developed it a little bit since then. So tin, you think of tin as being metallic. In the beta phase, it's metallic. It goes superconducting. It has a transition temperature of 3.7 Kelvin. So below that, it goes superconducting. It has a critical field of about 4 Tesla, a critical current 10 to 30 microamps. So it's a reasonable material. It also has, it's got quite a small gap. Delta equals 0.7 MeV. So when it's in the superconducting phase, it has a small gap. And I'm just showing you a publication here from 2021. That's my collaborators in California. They grow this material. They published a paper on this in the region of quantum computing. They can grow tin on indium antimonide. This is in the beta phase, but it also grows in the alpha phase. If it's grown at low temperatures, the tin can go down in the so-called alpha phase. And it's a small band gap semi-metal in the alpha phase. So I asked the question, when Ximena was here, we asked the question, what's the carrier density in alpha tin? We've got these tin wafers, tin on indium antimonide in the alpha phase. What's the carrier density? We were trying to measure the Hall effect in these systems. All right, my computer is not responding. Just to quickly show you the band structure in these materials, it's a so-called, it's got an inverted band structure. So the top of the conduction band is made of p states, and below that we have the s states. So the bands have kind of crossed over in this material. It's zero band gap. When you add strain to the system, the strain can open up a small band gap. So these materials, these alpha tin materials, they are grown on indium antimonide. So it's the same indium antimonide that that I've talked about earlier. It's acting as a substrate for the tin, and tin has a slightly different lattice constant. So we can build in a strain into this material. Depending on the size of the strain, the alpha tin lattice constant is larger, so it has to be a compressive strain in the system to grow epitaxially on indium antimonide. It has to be compressively strained, but it's compressively strained in plane. So the outer plane component is a tensile strain. So the outer plane component should go over to should send the system into something like a Dirac semimetal. So something that looks a little bit like graphene. It should go over to something like graphene. So strain is important in these materials. It turns out it's unavoidable. You have to grow it on some substrate. So the strain aspect will be unavoidable. It's possible to grow single crystal epitaxial tin on indium antimonide. a little bit of the problem is you can't heat the material up. If you heat the material up, it changes phase into the beta phase, which is metallic. So it has a phase change, and that phase change is just one, it's a non-reversible phase change. So we have to do everything at low temperatures. We have to process the devices at low temperatures. Here's just Here's just an optical image of a device. These are ohmic contacts. We use dilute HCl to make a hall bar. So this is our hall bar. This is a channel where we would pass a current. These are aluminium ohmic contacts. So they're contacts that we would use to pass a current through the structure. What we've also done is we can pattern the device. So we use the gallium ion beam patterning now. So it's the same system. It's this 30 keV gallium system to pattern almost nanostructures. They're kind of microstructures. So we can pattern microstructures into this material now. And as I've said, the lithography is quite a challenge. We have to use less than 60 degrees, so we can't cure resists. We can't put down dielectrics. It's a difficult material to work with. Though there is an array of wires, some transport measurements on an array of wires, it was really just to demonstrate, can we make wires in a controllable way? There's very little information in the device here. It's mainly, this is magnetic field now, this is device resistance as a function of magnetic field. So at least this technique has created this system that's not insulating. Okay. I'll skip that. I'm sorry. So what happens at low temperatures? This was data I took in the summertime. This is now cooling a device down to 70 millikelvin. And what happened is, this is device resistance now as a function of magnetic field up to 10 Tesla. What happens at low temperatures is we get some current going through the indium antimonide substrate, and then the indium antimonide substrate goes through this metal insulator transition that I discussed, and we're just left with the tin. And what we can see is we can see magneto oscillations in the tin. This is due to the Shubnikov-de Haas effect. If we expand those oscillations up, we see a whole series of minima here. What we also see in the material is something that looks like a spin splitting. So we get extra periods coming in here, but also that envelope seems to beat. There seems to be a kind of two frequencies that are matched. And if we do a Fourier transform of that, so what we show you here now is the Fourier transform of these oscillations. You can see the main peak has split into two, and it looks like a kind of a rash bar spin splitting. Now, that's interesting. What we also found is that the minima here, the minima in the Shubnikov-de Haas effect, the minima, which are filling factors, the integer filling factors don't correspond to minima in the magnetoresistance. These minima correspond to half integers. So the minima in resistance correspond to half integers. And we can kind of plot that out. They're a harmonic series. We can plot that out. So we can plot the half integer on the y-axis as a function of 1 over magnetic field. That gives us this harmonic relationship. But it turns out this n minus a half, this is a phase, an extra phase coming in. So we've got this extra phase coming into the oscillations due to the topology in the system. So we have this topological phase coming into the system. So that tells us straight away that it's not a bulk tin band. It's a band coming from this topological state in the surface region. So it was kind of quite an interesting result to get this. We were quite lucky to get this result. The mobility is about 4,000. So still quite a low mobility. So in terms of making a ballistic quantum wire, we're orders of magnitude away from that in mobility. I also looked at a second device. So this was a second wafer, and you can see on the bottom left here, this is actually Hall effect now. So Hall effect as a function of magnetic field, excuse me. And you can see here the oscillatory structure is much more complicated in this system. There are multiple frequencies. If you blow this data up, so this is an expanded scale now, you can see there are multiple frequencies going on. The only way to analyze this data is with a Fourier transform. If we Fourier transform this data, so that's the data on the bottom here. So this is Fourier transform power as a function of fundamental, as a function of fundamental field. So we can see this split peak that we'd seen. We knew in the other device that this peak had a Berry phase, but we've now also got these extra features coming out in this particular wafer. We have a second peak, so we have 3 peaks. We have 3 peaks in this system, 2 of which are topological, and they are also split. We also have this bulk peak here, which is not split. There's no spin splitting in the bulk, and there's no topological behavior. What we can also do in this Fourier transform is we can calculate the mobility. So we can get from the width of the Fourier transform, we can get the quantum mobility. And the quantum mobility here is about 9,000. So this particular wafer has a much higher mobility, and we've seen this extra structure coming in. The first wafer had about 4,000 mobility. As we've improved the material quality, the oscillatory structure coming from the surface state is much stronger, much more visible in the magnetoresistance. So just to summarize this, I've nearly finished my talk now. Just to summarize this, in tin, we see 3 bands of carriers. We'd like to be able to gate the structures so we can move the chemical potential in the region of interest where the bands are overlapping. As I say, they're 30 nanometer films, they're thin films, alpha tin. We've identified these 3 states. Now, it could be that the one of the states that we're seeing is a so-called L minimum. So that's a secondary minimum in the conduction band that's close to the chemical potential, accidentally close to the chemical potential. We could have a bulk heavy hole state possibly coming in. But we've also got this topological surface state. We know we've got this topological surface state because it has this Berry phase of pi from the magnetoresistance. So just to summarize what I've told you today, I've told you about suspended and disordered indium gallium arsenide structures. I told you about the high mobility structures as well, where we want to make a spin FET device with the University of California. I've introduced gallium ion beam patterning into indium antimonide, so we can pattern disorder into our structures. I've told you about the multi-connected devices, the anti-dot arrays, and looking at the phase in the wave function. I've also just finished by telling you about tin. I didn't mention bismuth. We've got data on bismuth. So that's that. Future developments, I want to use other focused ion beams. We can use helium and neon. Perhaps they don't introduce as much damage, which may be good for patterning wires and quantum wires or quantum dots. I've applied to a high field lab in Grenoble. We have a good relationship with Grenoble. We have 30 Tesla or 35 Tesla now, I think, on offer. I'm trying to sort out backgating. If you have control over the backgating, you have much more control over the electrostatics of the wave function confinement in the system. I want to develop further these phase coherent structures. I also want to develop strain. So if you bond your device to a piezoelectric crystal, by applying a voltage, you can change the strain in the layer. So we know in the tin, particularly in the tin, the strain is very, very important. And I actually applied for funding. I applied for funding on this to our national body for funding, the EPSRC. So hopefully that funding will come through. Just to finish off, lots of people involved in this work. As I said earlier, we had Ximena involved when she was working in Cambridge. We also work, we've got my colleagues here in UCL, Professor Pepper's group at UCL. We've got Professor Ritchie's group in Cambridge, and we have Professor Palmstrong's group that provide material from the Quantum Foundry. And I think I'll stop there.
Thank you, Professor Stuart, for your incredible talk. Now, well, in Spanish. Ahora vamos con las diferentes preguntas que tengan en el público. También los invitamos en las diferentes redes sociales que siguen por medio de las universidades a dejar sus preguntas para al final pues darlas aquí a conocer. Vamos con... iríamos con la profesora Maggie.
Hola, buenas. Buenas. Thank you very much for your talk. It was very interesting. It's not my subject, so I don't understand some things. But I have a colleague here that works with the heat transfer at the nanoscale. So I'm going to give him the link to the Facebook talk. So maybe he will have some question.
Thank you.
I'm sure he will be
Absolutely.
interested. And I only have one question. At the beginning, you have shown in one of your slides some SEMPIC images of the. It was before slide 9, but I'm not sure which one. One of your suspended films, and you shown some of the defects, and in one of them you had like a perfect crack, like with a small gap in between, but it was like really perfect crack, like it was just divided in two. So I was wondering if this kind of I was wondering if you could do that on purpose, like have such defect on purpose, and if maybe this kind of defect, like having this crack and just I don't know what's the space in between the two resulting films. Can you use that structure as a sensor, maybe? Like you can maybe immobilize some molecule, like biomolecules or biomarkers in between, and use this structure as a sensor?
Yes, I think that could be done. I think you would have to make an array, and they would kind of crack, and then you could kind of, if you make a 10 by 10 array, you might be able to get some structures which would be suitable. I think the problem is, when you etch them, you get the surface tension of the etch. When the bubble kind of collapses down, it brings the wafer down. So it's not very controllable. I think maybe with some more time in the clean room looking at this, you could get it more controllable. If you could get it more controllable, I could imagine then using it for a further device, putting some molecules on the surface or something freestanding. But at the moment, it just sometimes happens that everything just collapses down and cracks.
But could you maybe control the surface tension with some, if you functionalize somehow the structure? I mean, if it's a problem of surface tension, maybe.
Yeah, I think it would have to be looked at by, in the clean room. So it would be a kind of a clean room project where you would look at this effect. Maybe use different liquids, how they're dry. Sometimes how they're dried is important as to how they, how the structure forms. It's a good question. I think that there's a possibility with that.
Yeah, maybe they don't even need a liquid. Maybe just some vapor of some substance.
Yeah. I mean, we were quite surprised that this worked when we first started using this technique. We were really surprised that it worked. We just thought everything would collapse down. But these layers, they have this strain in them. And so sometimes they kind of spring up. It's like a pre-stressed concrete. In construction of concrete, they use pre-stress. So it's a little bit like that, but on a nano scale. So I think there's still work to be done on this.
Some colleagues from I collaborated with some colleagues from Tecnológico de Monterrey, and they work with the professor from Irvine in California, and they work with suspended carbon nanofibers and,
Really?
a nano gap in between.
Yes.
So it kind of remind me of that.
Yes. That would be nice work. Yes.
Yeah, it's the professor is the name of the professor in Irvine is Mark Madu. He maybe could be.
What was the surname, Mark?
Madu. Madu.
Oh.
Yeah. Okay.
I can look up the work. Thank you.
Thank you. Bye.
Gracias, profesora Maggie, por su pregunta. Vamos con el profesor Robert Guzmán.
Hello, Professor Stuart.
Hi, Robert.
Thank you for for me, it's an interesting topic, but I don't know about a specific thing of the world. First, do you work with gallium, indium, these kind of materials of the group 3 and 5 of the periodic table?
Yes. So we use indium gallium arsenide. Yes.
Yes. My question is about DFT calculations. I did some DFT calculations and I put some impurities of fluor or hydrogen, and my results say that the gallium breaks down the bond between gallium arsenide or between indium arsenide. I don't know that maybe this happened in experiments, in experimental physics. Do you suffer something like that in your laboratory?
That is a process that we try to avoid. So if we're damaging the materials, we try to avoid that, because that would be a very high energy. That would make the crystal insulating at room temperature. We try to avoid that if we can. That process. I believe that process can go on, but we try to avoid that with our damage, with our level of damage.
Usually in your laboratory are very clean. You don't put the impurities. You extract all the impurities.
So I mentioned several things here. One is no impurities. So they're very, very clean systems. Modulation doped, low doping density. And then the second is we introduce doping because doping gives us disorder. And we want the disorder to study the hopping effect in these materials. So I mentioned several fields here. So there's a range of disorder. Yeah.
Thank you, Professor.
Thank you, Robert, for your question.
Another question is about you put some current in your devices, and you can see the quantum Coulomb blockade.
Yes.
I don't know exactly what is the necessary value or the specific heat in order to put current in your devices. For example, I know that if you had materials with a low specific heat, when you put a current, the material destroys. I don't know exactly what is the minimal specific heat and in which kind and what was the temperature that you work in your.
The measurements I showed where we see the Coulomb blockade is all at 50 millikelvin. So it's very, very low temperatures. So we know we're at sufficiently low temperatures to see this Coulomb blockade effect. I mean, the Coulomb blockade effect is a kind of a tunneling effect. But the system goes over to being totally dominated by this tunneling between anisotropic regions of maybe higher carrier density or lower disorder. And we see the very, very characteristic Coulomb blockade effect, which is a tunneling effect. Did that answer your question? We tend not to measure specific heats. We tend not to measure specific heats. Some of my colleagues do those kind of thermal measurements. They do things like thermal power measurements. So it's not a specific heat, but it's related to, say, measuring the Seebeck coefficient, that kind of thing.
The current is about, for example, in your experiments of hollow blockade.
It's in nanoamps. It's nanoamps.
Nanoamperes.
Yeah, nanoamperes.
Okay.
Yeah, it's very small.
Okay.
Yeah.
Thank you. With this information for me, it's enough in order to estimate the heat received. And another question is so important because you show that you show at the beginning of your third part of your lecture that with pressure you can obtain a topological insulator. Yes?
Yeah.
What is the how many pressure you need to put in this hypothetical or real material? And another question is, do you can see current at the edge of the material or current a topological current in the edge of the material? Because I know that this is an important property of topological insulator.
Yes. So in terms of the pressure, we're at kilobar. The kind of the inbuilt pressure in the material is in the kilobar region. This is in the tin, right? We do see the current at the edge. So in the suspended in-gas devices, we see the quantum Hall effect, where we know the current is carried by edge states. We can interfere with that effect with a current, with a large heating current, and we can break down that effect. So we know in the in-gas, we have current by edge state transport. What we see in the tin is we see this Bury phase developing. So it's a different material system, same type of measurement, quantum Hall type measurement, but we see this Bury phase. So we know that if we compare with theory, we have this topological state. There the understanding stops. Experimentally, the understanding stops at this point. Then we rely on theory. Is it a 2D? Is it a 3D? Where are these states in the band structure? What are their makeup? Are they electron-like or hole-like? We know very little. Until we can get the gating and move the chemical potential in the system, or the Fermi energy in the system, we know very little else about the properties of these. So that's a good question. We don't know specifically if they're edge states in 2D or not.
Professor,
That's a good question.
It's interesting for us. And Professor, the last question is about academic question. You are engineering, yes? Engineering? Yes. I am physician. But I know that the mesoscopic physics join us.
Yes. Absolutely.
The mesoscopic physics join us. Professor, what kind of wood or material do you recommend in order to understand this specific process, column blockade, topological insulators, systems in a mesoscope between macroscopic and microscopic behavior? What kind of review of woods, something like that?
A lot of the early physics in this field was done in the gallium arsenide, aluminium gallium arsenide system. So all the past literature on mesoscopic effects, quantization of the conductance, quantum dots, Coulomb blockade, all the kind of physics-based understanding of these materials was done in gallium arsenide and aluminium gallium arsenide. And when you look at those systems now, you can very easily control thicknesses, doping levels, how the potential is set up to confine charge. It's very well controlled. So that is the go-to material system for studying these effects. The problem is, in this material, the things like the spin-related, electron spin-related effects tend to be very small. So that material system doesn't show very, very strong spin effects without high magnetic fields. So it's a trade-off. If you want to see other effects, you have to introduce some spin properties with a different material system. So there lies the problem. You have to compromise. You have to compromise generally on electrical material quality. Once you move away from gallium arsenide, the quality of the material is just not as good. So the effects seem to be weaker. Gallium arsenide.
Thank you, Professor, for your lecture.
Muchísimas gracias, profesor Robert, por sus preguntas. Vamos a continuar con nuestro siguiente. Aquí nos escribe el profesor Isaías que él no tiene preguntas. Vamos con el profesor José Fermín.
Hi, Stuart.
Hi, how's
Nice to see you today. Gracias.
Yeah, nice to see you.
Stuart, I have no questions for you today. Very nice. Maybe I will write to you in order you to send me your presentation.
Yes, I can do that. Yeah, please do.
Okay.
Yes, thank you.
Thank you.
Totally, please do. Yes, thank you.
Muchísimas gracias, profesor José Fermín. Bueno, también nos había escrito el profesor Luis que no tiene preguntas. Sin embargo, ahorita miramos si de pronto tiene algún comentario o cosa adicional que nos quiera comentar.
Yes. Thank you, Ximena. Thank you. It's a very nice talk. Just wondering about the temperature that you work there, and it is mostly are in room temperature, right?
The measurements.
Some of them
most of the measurements are low temperature.
Yeah.
We go to. I mean, the lab that you see me in Cambridge is 1.5 Kelvin, and that would be considered quite warm. So some of the data I showed you, done in London, in the LCN in London, is at 30 millikelvin, 0.3. So very low temperatures. So we need to go to the low temperatures to see these effects.
Yes, I saw that your equipment in Cambridge has a low temperature, and you told me as well that in order to have better applied fields, you turn to the UCL in London for the applied field measurements. And have you? I know that those materials are not magnetic at themselves, but have you tried applying some fields and even try to change in the angles applied field or some other?
Yeah, we'd like to do that because some of these materials, particularly the tin, we don't know if it's a 2D or a 3D conduction. If it's a bulk 3D, it won't really matter how you apply the field because it's bulk. If it's a 2D system, things should scale with the cosine of the angle. As you tilt through theta, it should scale as the cosine of the angle, the perpendicular field. So
have you tried that? Have you tried that on your devices?
No, not. We can do that in Grenoble, in the high field lab in Grenoble. But the problem with the fridge is, if you have a rotator, you tend to warm up the fridge as it moves around. It tends to warm up the fridge.
Exactly.
So there are people that do this, and I have to say it's a fairly standard measurement, but it does cause heating problems.
Okay, nice. Thank you. Well, I want to mention. Yeah. Thank you. I want to mention also that in Spanish for the public, por el público, de los miembros de la red y la comunidad latinoamericana, esta red también nos encargamos de hacer pasantías entre universidades de miembros de la red y el año pasado estuvo la tesista de doctorado Ximena Velázquez en la Universidad de Cambridge, justamente trabajando con el profesor Stuart Holmes. El año pasado y este año también el candidato a doctor Henry Sánchez de la Universidad Nacional Mayor de San Marcos de Perú en la Universidad de Cambridge, y ahora ha llegado también una nueva estudiante visitando la Universidad de Cambridge, que es Eliana, que está conectada. Eliana, are you here? ¿Que está conectada? Sí. Soon, Stuart Holmes is going to visit your office there, okay? Yeah. Okay. Nice. Eso solamente, y thank you very much for your talk. And Ximena, you are going now.
Thank you, Professor Luis. Bueno, revisando las redes de aquí de la Universidad Nacional de Colombia, no tenemos preguntas. Here we don't have question for Professor Stuart, but only they say, let me see. Well, congratulations for your talk, and that is a great topic. Now, in Spanish, James, ¿hay preguntas de la Universidad Mayor de San Marcos?
Hola, gracias por el paso, Jimena. Profesor Stuart, no tenemos preguntas de público, solo agradecimientos por su presentación. Gracias.
In Universidad Mayor de San Marcos, they don't have questions for you. Bien, ahora vamos a despedir al profesor Stuart, sin antes de que el profesor nos dé unas palabras de despedida. Now, Professor Stuart, could you say some words for say goodbye?
Yeah, well, thank you everybody for listening to my talk, and apologies if I went a little bit quickly. Apologies it wasn't in Spanish. My Spanish is improving very slowly. But thank you for listening, and also thank you for inviting me to give a talk to this format, to LAFMAT. Thank you.
Thank you, Professor Stuart.